Breakthrough: Webb telescope spots gravitationally lensed supernova, resolving the Hubble tension puzzle. The James Webb Space Telescope, JWST, a marvel of modern space exploration, has made a groundbreaking discovery that may finally offer a solution to one of the biggest mysteries in cosmology, the Hubble tension. For years, scientists have grappled with conflicting measurements of the universe's expansion rate, a problem that has puzzled the scientific community and raised questions about the standard model of cosmology. Webb's recent observation of a gravitationally lensed supernova has the potential to shed new light on this issue and bring us closer to resolving the Hubble tension once and for all. The Hubble tension, a cosmological puzzle. The universe is expanding, a fact discovered by Edwin Hubble in the 1920s. This expansion is quantified by the Hubble constant, h, which describes the rate at which galaxies are moving away from each other as the universe stretches over time. However, there is a perplexing problem. Different methods of measuring the Hubble constant give significantly different values. There are two main ways to measure the Hubble constant. The first is to observe the local universe, focusing on objects like Cepheid variable stars and Type I supernovae, which serve as standard candles. These objects have known intrinsic brightness, and by comparing their observed brightness, scientists can calculate their distance from Earth and, thus, the expansion rate of the universe. This local method typically yields a Hubble constant of around 73 kilometers per second per megaparsec, km/s/mpc. The second method involves observing the early universe through the cosmic microwave background, CMB, the afterglow of the Big Bang. By analyzing the CMB and using the standard model of cosmology, scientists can infer the expansion rate of the universe during its infancy, which provides a value for h of around 67 kilometers per second per mpc. The tension arises from the fact that these two measurements, one based on the local universe and the other based on the early universe, do not agree, despite both being highly precise. This discrepancy, known as the Hubble tension, suggests that either there is a systematic error in one or both of the measurements, or, more intriguingly, that new physics may be required to explain the difference. Gravitational lensing, a new cosmic tool. One of the most promising tools for addressing the Hubble tension is gravitational lensing, a phenomenon predicted by Einstein's general theory of relativity. When a massive object, such as a galaxy or galaxy cluster, lies between Earth and a more distant object, it can bend the light from that distant object, effectively creating a cosmic, magnifying glass. This results in multiple images of the distant object or distortions that can be observed by telescopes. Gravitational lensing can also cause time delays between the arrival of light from different images of the same event. For example, in the case of a gravitationally lensed supernova, light traveling along different paths around the lensing object will take different amounts of time to reach Earth. By measuring these time delays and understanding the mass distribution of the lens, astronomers can derive precise distances to the lensed supernova. These measurements can then be used to calculate the Hubble constant, independent of traditional methods. Webb's discovery, a gravitationally lensed supernova. The James Webb Space Telescope's unparalleled sensitivity and resolution have allowed it to make a historic discovery, a gravitationally lensed Type I supernova in a distant galaxy. Type I supernovae are often referred to as standard candles because their intrinsic brightness is well understood, making them valuable tools for measuring cosmic distances. When such a supernova is gravitationally lensed, it presents a unique opportunity to refine distance measurements with extraordinary accuracy. The gravitational lensing of the supernova created multiple images of the event, each arriving at Earth at different times due to the varying paths the light took around the lensing mass. This discovery provides a new way to measure the expansion rate of the universe and potentially resolve the Hubble tension. Webb's ability to observe in the infrared spectrum, peering through cosmic dust and gas, allowed it to capture the lensed supernova with unprecedented detail. Its advanced instruments provided astronomers with high-resolution images and precise time-delay data, offering a new method to calculate the Hubble constant and compare it with values obtained from other methods. Solving the Hubble tension with lensed supernovae. The discovery of a gravitationally lensed supernova by Webb could prove to be a turning point in the quest to resolve the Hubble tension. One of the primary sources of uncertainty in traditional measurements of the Hubble constant is the calibration of the local distance ladder, which relies on objects like Cepheid variables and Type I supernovae. These measurements, while precise, are prone to systematic errors related to the calibration of distances and the intrinsic properties of the standard candles. Gravitational lensing offers a way to bypass many of these uncertainties. The time delay method provides a direct measurement of the distance to the lensed supernova, which can be used to derive the Hubble constant without relying on local calibrations. This makes gravitational lensing an independent and potentially more reliable method for determining the expansion rate of the universe. If the Hubble constant derived from the lensed supernova matches the value obtained from the cosmic microwave background, it would suggest that the discrepancy in the local measurements is due to systematic errors, potentially resolving the Hubble tension. On the other hand, if the value matches the local measurement, it would indicate that there is something wrong with the early universe measurement, possibly pointing to new physics beyond the standard model of cosmology. The implications for cosmology. Webb's discovery of a gravitationally lensed supernova has far-reaching implications for cosmology. If this discovery helps resolve the Hubble tension, it would confirm that our current understanding of the universe is fundamentally sound, and that the discrepancy between the different measurements is due to previously unaccounted for errors. However, if the tension persists even after incorporating the new data from lensed supernovae, it could indicate that new physics is required to explain the difference. This might suggest that our current understanding of dark energy, dark matter, or even the nature of space and time itself is incomplete. The Hubble tension could be a clue that the universe behaves in ways that are not yet fully understood, and Webb's findings may be the key to unlocking these mysteries. The future of gravitational lensing and JWST. The James Webb Space Telescope's ability to observe distant, gravitationally lensed objects with such precision opens up new avenues for research in cosmology. Webb's instruments are not only capable of detecting lensed supernovae, but they are also designed to observe other lensed phenomena, such as quasars and distant galaxies. These observations will provide additional data points for measuring the expansion rate of the universe and refining our understanding of cosmology. The discovery of a lensed supernova is just the beginning. Future observations of additional lensed supernovae could help astronomers further refine their measurements of the Hubble constant and offer new insights into the nature of dark matter and dark energy. Gravitational lensing can also be used to study the distribution of dark matter in galaxy clusters, which plays a crucial role in shaping the universe on large scales. In addition to its contributions to gravitational lensing, Webb's infrared capabilities will allow it to study the earliest galaxies, probe the atmospheres of exoplanets, and explore the formation of stars and planetary systems. As the telescope continues to deliver groundbreaking discoveries, it is expected to revolutionize our understanding of the universe and answer some of the most profound questions in science. Conclusion: a path forward in resolving the Hubble tension. The James Webb Space Telescope's discovery of a gravitationally lensed supernova marks a significant milestone in the effort to resolve the Hubble tension. By providing an independent method for measuring the expansion rate of the universe, this discovery offers a fresh perspective on one of the most pressing issues in modern cosmology. Whether the Hubble tension is ultimately resolved through this new data or whether it points to new physics beyond the standard model, Webb's findings will have a profound impact on our understanding of the universe. As scientists continue to analyze the data from this and future observations, the JWST stands poised to unlock new insights into the nature of space, time, and the fundamental forces that govern the cosmos. With each new discovery, we move one step closer to solving the mysteries of the universe. The combined power of gravitational lensing and Webb's advanced capabilities offers a promising path forward in resolving the Hubble tension and deepening our understanding of the cosmos. The future of cosmology looks brighter than ever, thanks to the groundbreaking discoveries made by the James Webb Space Telescope.